All right, so for this example problem, it says, with much fanfare from the Brigade of Midshipmen, the USNA administration finally agrees to convert Worden Field into a parking lot. The parking lot will be 150 yards long, 280 yards wide, and half a yard thick. How much gravel, sand, cement, and water will USNA need for this project in tons, assuming a specific weight of concrete of 150 pounds per foot cubed? So every midshipman's dream is finally going to be realized. So we're given the dimensions of this parking lot, and we're given the weight of concrete, and we want to find the weight of gravel, sand, cement, and water. So the first thing we're going to do is we're going to find the total weight of concrete that we actually need. Now, weight is just equal to the volume of something times its specific weight. Now, since this is being set up as a field that's just length times width times height, because it's a rectangle, we can say that's length, width, height times specific weight of concrete. So we can go ahead and plug in all of our values. The weight of concrete will be equal to the length of 150 yards times the width of 280 yards times the height of 0.5 yards times the specific weight of 150 pounds per foot cubed. And then we're going to do some unit conversions, right? Because our dimensions are in yards cubed on top and feet cubed on the bottom. So we need to do 3 feet per 1 yard, and that's cubed. Alternatively, you can know that there's 27 cubic feet in a cubic yard. That's also acceptable. And then lastly, since our answer is going to have to be in tons anyway, I'm just going to go ahead and convert 2,000 pounds is 1 ton. And we get a total weight of concrete of 42,525 tons. So now we need to get around to using this 3-2-1.5 rule, right? So as a reminder, that means that concrete for this class, and in most cases, is approximately 3 parts gravel, 3 parts gravel, or coarse aggregate, to 2 parts sand, or our fine aggregate, to 1 part cement, to 0.5 parts of water. Well now, so how does that help us? How do we use this 3-to-1.5 ratio to actually go about calculating how much of each of these things we need? So I'm actually going to take a step back from it and look at a simpler problem. So let's say we were making pancakes, right? And you looked at your recipe, and your recipe told you that your pancakes were 1 part flour to 1 part milk for the mix. And if I told you I wanted 1 gallon of pancake mix, you'd be able to see pretty easily right away that, hey, if I need a gallon and it's a 1-to-1 ratio, that means I need half a gallon of flour to half a gallon of milk. Right now, hopefully everyone can just jump to see that pretty quickly based on their experiences over the last 20 odd years of their life. Now, if that recipe were 1 part flour to 1 part milk to 1 part egg, and I still needed 1 gallon of total mix, most of you would just jump ahead and just be like, hey, that means 1/3 of a gallon, 1/3 of a gallon, 1/3 of a gallon if I want, again, still 1 gallon total, right? And where it starts getting a little interesting is if you say instead of 1-to-1-to-1, it were 2 parts flour to 1 part milk to 1 part egg. Most of you would still pretty much just jump ahead and say, hey, that means that half of my mix is flour, so I need a half a gallon of flour and 1/4 of a gallon each of milk and egg. So what we have to do is we have to step back and see what math are you doing intuitively to figure out those numbers? Because if you can figure out what math that is that you're doing intuitively, well, we can apply it to this concrete mix, or in reality, everything else you're going to cook for the rest of your life, or all kinds of ratios you're going to end up having to do on your ship, submarine, aircraft, or Marine Corps platoon. And if you can figure that out, then we can go ahead and convert it pretty easily. So let's take the flour, for example. So you can see 2 parts to 1 part to 1 part. The flour should end up being half of the total. So where's that coming from? You're taking the amount that you want, 1 gallon, and you're multiplying it by the number of parts of flour divided by the total number of parts. So what that's doing for you is you're taking 1 gallon and you're multiplying it times 2/4, which is half. When you were doing it for milk, you're doing 1/4. When you're doing egg, you're doing 1/4. And if you went back to our 1:1:1 ratios, you could see that the total number of parts in that case was 3. So each thing ended up being 1/3. So now how does this work out for concrete? Well, since we have 3, 2, 1, and 0.5, our total number of parts is 6.5. And then for each of those individual pieces, the ratio would end up being 3 6.5ths of the total weight for gravel, 2 6.5ths of the total weight for sand. So it's the exact same process as you use with something simpler. It's just a slightly odder number because it adds up to 6.5 total parts. So let's see what this looks like when we actually do all of our math. So I'm going to show you how I do these problems, which is kind of sequential, where I set up every single one of these equations and then I'm just going to solve them all straight down the line really quickly. So we know we want the weight of gravel, we want the weight of sand, we want the weight of cement, and we want the weight of water, right? So each of those is going to be equal to the total weight of concrete, C-O-N-C-R-E-T-E, spelling is hard, concrete, and then we're going to have to multiply it by that ratio. So the parts of that thing divided by the total number of parts. So for gravel, we had 3-part gravel to 6.5 parts of concrete. Now I'm going to kind of abbreviate my spelling a little bit. So for the next, we had 2 parts sand to 6.5 part concrete. For cement, we had 1 part cement per 6.5 parts of concrete. And then for water, we had 0.5 parts water to 6.5 parts of concrete. So now we can go ahead and we can plug in our total weight of concrete, that 42,525 tons. Same for each. And then each one of these multiplied by 3 6.5ths, 2 6.5ths, 1 6.5th, and 0.5 6.5ths. And if you go through and you plug all that into your calculator, you're going to get 19,627 tons of gravel, 13,085 tons of sand. Let's make the 8 look a little bit nicer. 6,542 tons of cement, and 3,271 tons of water. And just to check our work, you could go through and you could add up all 4 of those numbers, and you can see that it adds up to the total weight of concrete that we wanted. So that's one way that you can kind of dummy check yourself to make sure that you get the right answer. So that process doesn't change for these concrete problems. Any of these concrete problems where you need to calculate how much of a certain constituent you need, you're going to calculate the total volume of concrete you need. You'll multiply by the specific weight of concrete to get the total weight of concrete that you need, and then you'll use the same 3:1.5 ratios in order to get whichever component you're looking for. And that's all there is to it.